So let's dive into some geometry. We're going to explore something you see every single day, but maybe don't think about all that much: the special types of quadrilaterals.
Okay, let's start with a shape we all know, right? The square. But have you ever really stopped to think about what makes a square, well, a square? I mean, what are the specific rules that make it different from, say, a rectangle or any other four-sided shape?
Well, the answer is actually pretty elegant. It's not just one thing. It's kind of like a beautiful family tree of rules, where each one builds on the last. And that's what we're going to do today. We're going to build these shapes together, right from the very beginning, one simple rule at a time.
So to get to the specialists, we've got to start at the top. Let's meet the head of the whole family.
Okay, so this is our starting point, the absolute base level. The only rule here is that it has to have four sides, and it has to be a closed shape. That's it. It could be a kite, a diamond, even a weird lopsided window frame. If it's got four sides, boom, it's a quadrilateral.
All right, now things start to get really interesting. We're going to add our very first rule, and trust me, it's a big one. It's all about something called parallelism.
So by adding just one little rule that exactly one pair of opposite sides has to be parallel, our basic quadrilateral gets a promotion. It levels up and becomes a trapezium. Now it's a shape with a specific, predictable quality. And you can see it perfectly right here. See how the top and bottom sides are running parallel? They're like train tracks. They'll just keep going forever and never cross. But the other two sides, hey, they can go off in whatever direction they want. That's kind of the whole deal with the trapezium.
And this is really the heart of geometry. You take a shape, you figure out its rules, and then you just ask that simple question. Okay, but what happens if we add just one more rule?
So let's do it. Let's level up again. We take that trapezium, and now we make the other pair of sides parallel too. And just like that, poof, we've created something way more balanced and structured. We've got ourselves a parallelogram.
So take a look. Now both pairs of opposite sides are parallel. And this one simple change, it has some really amazing consequences that we're about to get into. And I really do mean powerful, because that one little change, going from one set of parallel sides to two, it doesn't just change the name on the box. It automatically gives the shape a whole bunch of new properties. It's almost like it unlocks superpowers. And what's so cool about this is that these aren't new rules we had to add. Nope, they are just natural consequences of having those two pairs of parallel sides. Suddenly, the opposite sides are equal, the opposite angles are equal, and the diagonals, they slice each other perfectly in half. They bisect each other, right in the middle.
But that's a fair question, isn't it? How can we be so sure that every single parallelogram in the entire universe, no matter how big or small or tilted it is going to have these exact same properties? Well, the answer is just, it's in the beauty of a geometric proof.
See, the whole secret is in the triangles. If you just draw a line, a diagonal, slicing that parallelogram in half, you get two triangles. And the key is, you can prove those two triangles are completely identical. And if the triangles are identical, well, then their matching sides and angles have to be identical too. It's such a clean, simple way to prove that these properties are true every single time.
Okay, so the parallelogram is our new souped-up starting point. Now let's see what happens when we add just one more specific rule. This is where the family tree branches off. We get two specialists, two distinct children of the parallelogram. So here we are at a fork in the road. We can take our parallelogram and force all its angles to be perfect 90-degree right angles. When we do that, we get a rectangle. Or we could go another way. We can let it keep its tilt, but force all its sides to be the exact same length. And that gives us a rhombus. See? Two different rules, two totally different shapes. And here they are, side by side. You've got the rectangle with those strong, perfect corners. It's all about stability. Then you have the rhombus with its perfectly equal sides. That's all about balance. Both of them are still parallelograms. Deep down, they've just picked different ways to specialize. Okay, so we've added rules about parallel sides. We've added rules about angles. We've added rules about side lengths. So what happens if a shape comes along that follows all of the rules? Well, then you get the apex predator of the quadrilateral world. The square. It's the shape that just has it all. It takes the parallel sides from its parent, the parallelogram.
It takes the 90-degree angles from its sibling, the rectangle, and it takes the equal sides from its other sibling, the rhombus. It's the perfect combination of every single rule we've talked about.
And this is what makes the square the king of the castle. I mean, think about it. A square is a parallelogram, it is a rectangle, and it is a rhombus, all at the same time. It has every single power of its ancestors, which makes it the most versatile and, yeah, the most powerful shape in the whole family. And since it's a member of all these different clubs, it gets all the perks, right? It inherits every single superpower we've talked about. Equal sides, right angles, diagonals that are equal, and cross at perfect right angles. The square really, truly has it all. Okay, so this is a really cool family tree of shapes, but why does any of this matter? What's the point? Why do we bother proving all these properties? Well, it's because they give us the power to solve real problems with absolute certainty.
Here's a perfect example of what I'm talking about. Let's say we have a rectangle, and someone tells us that one half of a diagonal is 3x plus 3, and the other half is 2x plus 6. Now, normally, that might not mean much, but because we proved that the diagonals of a rectangle are not only equal, but they also cut each other in half, we know for a fact that those two little expressions must be equal to each other. So we can just set up a simple equation, solve for x, and we're done. The geometry gave us the key to unlock the algebra. It's that powerful.
So think about where we started. Just a simple, generic four-sided figure. And by adding one simple rule at a time, we built this entire system of predictable, powerful shapes. It really makes you wonder, doesn't it? What other complex things out there, in nature, in technology, maybe even in our own lives, are built on just a few simple, elegant rules, just waiting for us to find them?